Hello everyone, my name is Fardin Sharif. I'm civil engineering PhD student at Lakehead University under the supervision of Dr. Amir Azimi. My topic is experimental study of sand-water coaxial jets with a low velocity ratio in 2021 CSCE annual conference. So, I start this presentation with a brief background description. A single-phase turbulent jet occurs when a moving fluid enters the quiescent body of the same fluid, causing a velocity shear rate. By introducing solid particles as a second phase in a water jet, other water jets, particles laden or slurry jets can be formed. A coaxial jet is comprised of two inner and outer annular concentric jets employing as a method to enhance the mixing capability of different outlet streams. Sand-water turbulent jets are commonly used in many engineering applications, such as an effective method of reclaiming tailing ponds in oil industry, dredging material, and building artificial islands. Let's move on to the objectives. How can the study of the sand-laden jets help in proper design of jets, optimizing the existing discharge systems by adding annular stream, sand-water mixing property enhancement, and finally the key parameters are particle size, concentration, nozzle diameter, velocity ratio of annular to the central stream. Let's move on to experimental setup and coaxial jet assembly. All experiments were carried out in a rectangular tank as shown in this slide. The core nozzle diameter of the funnel and the concentric annular diameter were 6 mm and 12 mm respectively. The water was discharged through the core nozzle and sand particles with a size of 0.386 mm was released through the funnel and discharged in the water with no initial premixing. The axial and radial distribution of the sand concentration and velocity were measured by an advanced optical fiber probe with two light sensors as shown. Therefore, the cross-correlation technique needs to be performed between two signals to obtain the instantaneous velocities. In addition, to investigate the flow properties such as mixing and periodic motion, higher frame rate snapshots were recorded by using a high-speed camera. In this section, the controlling parameters will be explained. The first one is Stokes number that characterizes the behavior of particles suspended in a fluid flow. Second parameter is Reynolds number, and finally is the mass flux, or the rate of a mass flow at the nozzle. For this study, the Stokes number was calculated based on the particle size and annular nozzle diameter, and it is roughly around 0.7. The experimental details and non-dimensional parameters are listed in table 1. The velocity ratios are in the range of 0 to 0.33. In this slide, we will talk about the signal processing. The signal processing toolbox in MATLAB software and the wavelet noise reduction toolbox were employed to do signal processing and to enhance the quality of the voltage signals. To obtain accurate signal velocity data, the cross-correlation technique was employed based on different segment sizes of voltage signals. As shown in figure number 1, it was found that the data uncertainty increased by decreasing the data segmentation size corresponding to 50% overlap. Therefore, a segment length of 2048 with no overlapping was selected for all the data in this study. In addition, each individual captured time average voltage signal by the probe's tip can be converted to the sand concentration through the calibration curve. Let's move on to the results. First of all, we will discuss about the axial sand concentration and velocities. Figure number 2 shows the effect of velocity ratio, which is between 0.16 to 0.33, and the variation of a normalized axial mean concentration and the velocity of the coaxial jets. It was found that the potential core of the sand water coaxial jet is 5 times of the nozzle diameter. Sand phase concentration and velocity are independent of the velocity ratio for x by d smaller than 16th. Decreasing the velocity ratio causes a higher velocity decay rate similar to the water jet. In this section, the radial sand concentration and velocity profiles will be discussed. So as you can see, all the data were normalized, and the velocity ratios are 0.16 and 0.21. As can be seen, all the velocity ratios and the radial concentration exhibited a near field hump at R by D 1.25, indicating a migration and mixing of the particles jets toward the jet's axis and reduction in intensity of the hump further downstream in the flow development zone for x by d smaller than 30. Also, increasing the velocity ratio led to the higher particle dispersion. Let's move on to photographical study and mixing properties. The high-speed images of sand water coaxial jet with various velocity ratios are shown in figure 5. As shown, for smaller velocity ratios, more uniform flow and the particle dispersion can be observed. To photographical study, a new method, spectra proper orthogonal decomposition, or SPOD, were employed to capture the influence of a particle on mixing and interscale coherent structures to find a most dominant structure in flow field in both space and frequency manner. The initial step to perform SPOD method is by adjusting a time series snapshots to construct a single data matrices using NP snapshots and MP pixels. Applying the SPOD algorithm based on the Welch periodogram method of temporal Fourier transform of the data, then the flow and particle oscillation can be decomposed to the temporal coefficients called eigenvalues, and they can be characterized by Kelvin-Helmholtz instabilities. So there is the SPOD results. It's performed based on the 1500 high-speed snapshots with 256 the size of a data blocks, and 50% overlap. As can be seen from the figure 6, the Kelvin-Helmholtz type wave packs can be distinguished. Also, the decreasing the velocity ratio, the wave pack turns to the axially elongated shape. And also, as can be seen in the figure 7, the large separation between the eigenvalues spectra is a good indicator of dominant mode and energy distribution and vortex shedding controlling the dynamic of the flow. And finally, conclusion. A series of laboratory experiments were carried out to investigate the effect of a low velocity ratio on the dynamic of sandwater coaxial jets with an advanced optical fiber probe. The initial mixing zone was found to be 5 times of a nozzle diameter. By decreasing the velocity ratio in the zone of a flow development, the decay rate increased accordingly and becomes similar to the single-phase water jets. The concentration decay rate was found to be smaller than the decay rate of a particle clouds and slurry jets. And also a near field hump was observed at R by D equals to 1.25 for all cases of concentration and velocity profile due to the high mixing of particles with a central water jet. And also a spectral analysis and SPOD measurement were employed, and it was observed that they can characterize by Kelvin-Helmholtz instabilities, and mostly the energy stored in first 10 modes. So these are our references, and thank you so much for having me. If you have any questions, I'll be here to answer all the questions.